So anyway, I'll leave you to answer that one. Now, the other thing that you cannot have is b as a negative number. And, on my graph here, when I try b as a negative number, it just it just disappears, right? Like there's nothing there at all. Um, so, let's try to just explore what's going on with b as a negative number for a sec. I'm going to draw. Let's see. I've never actually tried this. We'll see if this works. So I'm going to draw a sequence k, and let's make b to the k. K can be between the numbers -10 and +10, and it can count up by 0.1s. So if I make b a negative number, like let's say -2, something very, very bizarre happens. Okay, now let's try and make sense of what we're looking at. We have, so it kind of looks like a double-sided exponential, right? Like if we stretch this out a bit, make it a bit easier to see. Okay, and let's hide this text. It has exponential growth, but it also has like negative exponential growth. And if you draw 2 to the x, the positive one, and -2 to the x, the negative one, when you have a -2 as the base, and by the way, actually that reminds me, let's just write it out fairly clear. So I asked you this question earlier in the unit, but let's just make sure we talk about it now. Sorry, I just gotta find that thing is not the same as that thing, okay? And this is no more important than it is right now, because the function -2 to the x, which I've drawn here in blue, is perfectly fine. The function that I'm drawing in the dots is the one in brackets, -2 in brackets to the x. And you can see that this function, it exists, but it doesn't exist nearly in the same way that a regular one does. For starters, many of the points are not connected. So like there's a point at -10 and there's a point at -9. Let's get rid of this one again. There's a point at -8, -7, -6. So it's like it exists at all the integers, but it doesn't exist, right, at any of the decimals. When I try to put it in decimals, you can see GeoGebra just comes back with a question mark because it doesn't know how to do what I'm asking. So the function -2 to the power of x, certain points exist, but the function as a whole doesn't really exist, and it doesn't really make a lot of sense because it jumps from positive to negative, back to positive, back to negative, back to positive. Like it's a very unusual thing, and it really has nothing to do, or it really doesn't behave, let's say, very much like our other exponential functions. So what I'm going to write down for this is I'm going to say b must be positive, since if b is negative, right, the function becomes discontinuous, so it's just dots instead of a smooth curve, as many points do not exist. You might ask yourself, why not? Why don't they exist? And the function jumps from positive to negative repeatedly. So like it has a positive dot, then a negative, then a positive, then a negative. It really just does not work. And for the purposes of our class, we're just going to say if b is less than 0, if b is a negative number, we just don't have a function, right? When b is a positive number, we get all kinds of points, right? Get all these different points connected together. But as soon as b is a negative number, all of a sudden we just lose all those points, and it just becomes dots, right? And not only does it become dots, it becomes dots in the positive and the negative side at the same time. And so this is a something, but it's not an exponential function. So again, the exponential function, what we are calling exponential functions, are anything that looks like this, b to the x, as long as b is not 1 and as long as b is a positive number. Okay? Now, if you already used this word, but just to make sure we have a definition, an increasing interval means as the x values increase, the y values increase. So if you imagine yourself walking across the graph from left to right, so let's just get rid of this experiment here and go back to this one. An increasing interval would be you are walking uphill, whereas a decreasing interval would be you are walking downhill, right? You always read these graphs from left to right, so the y values decrease. Okay, A is a line that a curve approaches more and more closely. Again, what we're calling here is an asymptote. Right? And you can see that the exponential functions always do have an asymptote, and that asymptote is at y equals 0. Let me just give this a color and a style. Okay, that no matter what I put for the base, it always has that same asymptote of 0, which it approaches but never reaches. Okay, now basically for today, your job is to create graphs of all of these things. You know, I don't know how much of this is necessary to watch on a video and you can just kind of do on your own. Let's just... I think what we should do is, you know, I'll give you the points. We'll look at the graph and then, you know, you can draw it on your own time. So, first thing we're talking about today is doing exponential functions with a transformation parameter. So you notice here we're looking at a times b to the x. So a is the vertical stretch parameter. It's the same thing as what you already know from transformations. B is the base of the function. B is part of the parent. It is not a transformation. Okay, so b is not a transformation parameter. Remember the transformation parameters were a, k, d, and c. So a is a transformation parameter, and it is here. B is not a transformation parameter. It is part of the parent. So like this first function has a different parent than this one, and a different one than that one. Now 1 is already kind of a silly function. We've already looked at it. The common ratio for all terms, every term divided by the previous term is equal to 1. So the common ratio is 1. Again, what does this one look like? Let's just set b equal to 1. And you can see it's not really an exponential function. It's a linear function. So that's why we've restricted it from the domain. So it's linear. It's not really what we call exponential. It's just a flat line, right? Okay, now the y-intercept is 0, 1. The a value is a 1. It's not there. The b value is a 1. It's increasing, decreasing, or neither. It's neither. Okay. Let's look at this this next one. So the next one's 2 to the power of x. The y-intercept again is 0, 1, which is actually true for every function of the form b to the x. The a value is 1. I don't see an a value. B is 2. This function is increasing. And the y values go 1/4, 1/2, 1, 2, 4. Every term divided by the previous term equals 2. And the common ratio, if you haven't noticed, is equal to the base, the b value, right? Whatever the b value is the common ratio. Okay, again, just a quick look at 2 to the x. Okay, 2 to the x just looks like that. Again, the points I mentioned would be -2, f of -2, -1, f of -1, 0, and f of 0. One f of 1 and 2 f of 2. So stop this silly animation thing. Why it does that. Okay, so those are the 5 points it asked you to draw. The 5 points are the ones that we said it should have. Okay, so again, those are the 5 points. So negative 2 and 1/4, negative 1 and 0.5, 0, 1, 1 and 2, and then 2 and 4. Okay? And we go to the next one, 3 to the x. The a value, again, is not there. The b value is the base. That's 3. This function is also increasing. This is 1/9, 1 over 9, 1 over 3, 1, 3, and 9. And again, common ratio is equal to 3. Let's just show that quickly. B equals 3. You can see 1 over 9 is 1.11111. 1 over 3 is 0.33333. And then you have 1 comma 3 and 2 comma 9 are the other points, right? So you have all those 5 points that we wanted. So when b is greater than 1, the exponential function is always increasing. The horizontal asymptote is always y equals 0. And the y-intercept is always 0, 1. Okay, so this is like really helpful down here, right? All of this stuff is always holds true. Now down here, okay, we're going to look at a b value. So 2 questions where the b value is a fraction in between 0 and 1. So let's start with 1/2. So here b equals 0.5. Now, interestingly, the values you see here, 4, 2, 1, 0.5, and 1/4, are the exact same values we had and in the 2 to the x question, right? So go back up here. Like, see, 1/4, 1/2, 1, 2, 4. We have the exact same things, but in the reverse order. It's another really good question about, like, what is the relationship between these two graphs? Here's 2 to the power of x. Actually, I already had 2 to the power of x. So in red. Okay. And here's 1/2 to the power of x in green. How are the red and the green related? Well, you know, I think an obvious way these are related is that they are symmetrical left to right, right? And we know that to create left to right symmetry, you find wherever the x is in your equation and you make it negative, right? Because the k, remember k is what flips it from left to right, and k is the number right beside x. So if you draw 2 to the power of negative x, you get the same thing as 1/2 to the power of x, right? 0.5 to the power of x. So what we should write down here, we can write down 2 to the x is equal to, let's say 1/2 okay, is also equal to 2 to the negative x. Right? And that's a really important idea as well. That, and you know, we should realize this because, of course, 1/2 is 2 to the power of negative 1, and then you bring the negative inside the bracket and you got, you know, 2 to the x, right? So anyway, this one, the y-intercept is still 0, 1. That didn't move. The a value is 1. The b value is 0.5. I'm also going to say, or what we could say is 2 to the power of negative 1. That's a helpful way of thinking about this sometimes. Anyway, the common ratio here is 0.5. You take any term and divide it by the term before it, or 2 to the power of negative 1 is another way of writing it. Again, this one will work the same way. You have the intercept is 0, 1. The a value is 1. The b value is 1/3, or 3 to the negative 1. It is a decreasing function, as was the one above it. And the values are 1/9, 1/3, 1, 3, and 9. The common ratio is 1/3, or another way of saying 1/3 is 3 to the power of negative 1. Okay. When b is a number in between 0 and 1, the exponential function is decreasing. The horizontal asymptote is still y equals 0. The y-intercept is still 0, 1. Okay, so those things don't change but the function does change from increasing to decreasing. Okay, so for the last part here, we want to just do some brief experiments with an a value. So what happens if we have an a value? Okay, so let me just see. Just push this onto a new page so I have more room. Okay, so what if I add an a value to my model? So let's go back. Get rid of this. I think I can get rid of all of that. Get rid of that. Just keep some of these things though. Okay, what if I add a slider for a? And, sorry, not a text. Okay, and now what I want to do, I'm going to change my function. So instead of being b to the x, it's a times b to the x. So let's set b at 2. Okay, so here's your exponential function. Passes through 0, 1, 1, 2, 2, 4, and so on. If I change a, what happens? If I make a number bigger than 1, it stretches everything upward. If I make a number less than 1, it compresses everything downward. If I make a 0, obviously it becomes a flat line. And if I make a negative, it becomes, the function reflects from being only in the positive region to being only in the negative region. Now importantly, a is moving the y-intercept. So that 0, 1 is in a different place if there's an a value. So one of the things you can say here is that if you're looking at a function that does not go through 0, 1, you know it has to have a transformation, because every exponential function normally goes through 0, 1. So it must have been transformed if it didn't. So the first thing they're asking us to draw is 1/2 2 to the x. So let's draw 1/2. So I'm going to make a 0.5 and then multiply by 2 to the x. And what are the numbers we get now? We get 1/8, 1/4, 1/2, 1, and 2. So it's kind of like the same numbers, but they kind of got squished down by a factor of 2. Remember, the old graph would have been up here, and all the points would be twice as tall, right? But the new graph has been vertically compressed, so it's half as tall. The common ratio, though, is still b. The common ratio is still 2. If you take any term and divide by the term before it, you still get the b. So when you're looking at a transformed function, you can still find b doing that technique of comparing one term to the next. The y-intercept is now 0a, right, which is 0 and 0.5. A value is 0.5, b value is 2. This function is still increasing, okay, but more slowly than the parent would have. Okay, let's try this one. 3 times 1/2 to the x. So my b value is 0.5. My a value is 3. First of all, notice the y-intercept. It's not at 0, 1 anymore. It's at 0, 3. So this a value has stretched it up by a factor of 3. So again, the y-intercept is located at 0a, in this case 0, 3. The a value is 3. The b value is 0.5. This function is decreasing. Okay. Now what are the y values? Let's look at the y values. At -2, we have 12. It's not asking for -2, but okay, well, we'll start at -1. -1, we have 6. At 0, we have 3. At 1, we have a 1.5. And then at 2, we have 0.75. Now again, if you take any term and divide by the term before it, so for example, term 3, oh, I'm sorry, I'm making subscript. Term 3 divided by term 2, right? You're going to get b. You're going to get the base. And the base here is 0.5. For example, 3 divided by 6 is 0.5. 1.5 divided by 3 is 0.5. 0.75 divided by 1.5 is 0.5. So you still get the base every time you compare you compare one term with the next. Okay. Okay, the last one here is just a negative. So, and the 3 is to the power of negative x as well. So just be careful because there's two things going on in this question. The y-intercept for this one, so let's write it. So I'm going to put a as -1. Now for b, you might think I should put 3, but I'm not going to put 3 because that's actually not what this question is asking. It's not asking -3 to the power of x. It's saying -3 to the negative x. So again, let's use your knowledge here. Let's try and write this a different way with a positive exponent. So -3 negative x. If I asked you this 2 days ago and I said, this thing is driving me absolutely crazy today. Write with a positive exponent. Okay. If you want to write this with a positive exponent, the negative down here doesn't change. The exponent becomes positive, and the 3 becomes a 1/3. Right? That's how the negative exponent becomes positive. You flip the base over. So instead of 3 over 1, it's 1 over 3. So this is really what we're being asked to draw here. The a value is -1. The b value is 1/3. The y-intercept is going to be located at 0a, so in this case 0, -1. And the function is going to be decreasing. Actually, no, sorry. The function is going to be increasing. Let's draw it. So, a equals -1, b equals 1/3. I don't know why it has this feature where when you press spacebar it animates, and it's just not a good feature. b is equal to 1/3, a is equal to -1. Right, and it animates b as soon as I do that. Sorry. Okay. What are we looking at here? We're looking at exponential decay, but flipped over, right? So it's reflected so that instead of like coming down and approaching 0, it's coming up and approaching 0 from the negative side. Its y-intercept is still 0, -1, but that's because of the a value, right? The a value is -1. The y-intercept is whatever the a value is. And the points, what are the points we're supposed to get here? So we're supposed to start at -2. So at -2, it goes through -9. At -1, it goes through -3. At 0, it goes through -1. At 1, it goes through -1/3. And at 2, it goes through -1/9. Now again, if you take any term and divide it by the term before, you would get positive 1/3. Right? For example, -3 divided by -9 is positive 1/3. -1 divided by -3 is also positive 1/3, and so on. Okay? So that last one's a little bit tricky because of this negative sign up in the top, so be careful about that. Okay, again, use GeoGebra to graph them and double check your work, right? Plot your points and you can draw them out. So just to cover a few last things here. The domain of all the exponential functions is any real number. Now do not get this confused with the restrictions on b. b has some restrictions, but b is not the variable. b is part of the parent. Okay? The domain of the exponential function is any number. Any real number can be subbed into it. The range is any positive number. Not 0, but any positive number. So any number bigger than 0. The exponential function increases if b is greater than 1, and it decreases if b is between 0 and 1. It has a horizontal asymptote at 0 and a y-intercept of 1. Now, if it's being stretched, okay, the domain is not changed, but the range can change. Okay? Sometimes the range is all positive numbers. Sometimes the range is all negative numbers. The y-intercept is located at 0a. The horizontal asymptote is still y equals 0. It depends on decreasing and increasing whether it's reflected or not. So it's decreasing if b is bigger than 1 and you have a reflection. It's increasing if b is in between 0 and 1 and you have a reflection. So just try to remember that if you have a reflection, it's the opposite of what it would normally do. If a is greater than 1, it's vertically stretched. If a is in between 0 and 1, it's vertically compressed. And you can always use your mapping notation. X maps onto x, and y maps onto ay or ab to the x. You just multiply. Yeah, I mean just ay actually probably makes more sense. So if you have the parent, you can map using ay. I don't think that's really necessary now, but it may be necessary tomorrow. So there's a lot of good questions to try here. I think this first one is really good. Drawing them, of course, is good practice. And I like these kind of questions where I give you some conditions and then you're asked to draw a graph that fits. So that's something you might expect in communication.